All right. Okay. So welcome to the lecture on a topic that's kind of near and dear to my heart, this text to SQL. So I've actually worked in this area for a long time. It's one of my research areas from earlier. And I also have a company that's doing text to SQL. Please tell me this thing. Okay, that was fine. So, so the text to SQL problem. So the problem. So this is a kind of a common kind of pitch for why the problem is relevant. So what we have, I'm sorry, I'm going to close this window here because I'm getting traffic noise. That's probably a little bit better. So a kind of a common argument is that basically for text to SQL is that businesses a lot of times are collecting a lot of good data. So the data is being collected from people's activities in an SQL database. Or let's be honest, I mean, these people are using specialized tools, right? And then those specialized tools, so like this person here in accounting might be using a tool like Sage. And then there are like processes that copy this to the company level SQL database, which is kind of a lake over the entire operations of the company. So this architect here might be using some special like a CAD CAM, where this person is working on different projects, and that also gets copied out. I'm sorry, that gets copied out to the lake. And this is, that was accounting. This is different, different. There's the boss, I guess. I guess just a point. If they generate a report that the boss doesn't like, the best thing for the boss to do is just to fire them. Because if they're reporting bad data, it must mean that they're not loyal. So that's just kind of that's what Trump does. So big old Trump, he fires the messenger. So she better be careful here about running her accounting report. But anyways, that was a side joke. Yeah. So anyways, right. So everything winds up in some SQL system, and then what happens is that these people have questions that are kind of spanning these things. They want questions. The technical staff are kind of burdened with all these people's questions, and then they have to write the SQL themselves. So the technical staff is burdened with this they have questions they want to ask. They can put them into natural language. But then this person here has to translate those to SQL over the lake, and it's kind of like a big, either like there's a bottleneck there, and then because there's a bottleneck there, the data is not fully utilized. So there could be data that could be of relevance that is not coming out because of that. So if you have a text to SQL engine, the argument then basically is that frees up the technical person. And these people can simply just kind of query using natural language over the lake to get an idea of kind of what are the operations. And they can it's interesting because even if they have something like Sage, they have like a domain specific system, like for their accounting. Actually, a lot of times the lake, since this is kind of like a dedicated server, a lot of times this will be a lot faster to ask questions over than going through these kind of things. So a lot of times the UIs to different like SaaS tools are really cumbersome and they take a long time because the SaaS tool is basically adopting a tenant system, and they're overloading their servers and things are really slow. So I mean, I'm not sure if how much experience people have with this kind of stuff, but that kind of experience where I'm accessing our system and it's taking like forever. And the reason why is because the SaaS company they've got a whole bunch of other customers. They've tenanted on the same server, but usually the lake will run on your own server, so the access path here can be a lot quicker. Okay, but anyways, if you have text to SQL or something equivalent, then the argument is that basically this will allow for a more efficient kind of access into the, so text to SQL will facilitate seeing into the actual data quicker and presumably with more flexibility. Notice this is a back office example. So this is back office facing example. And this example here is like, okay, this would be more of a customer facing example. But the example here would be something kind of like using text to SQL to build an interface that people could like search for flights, like flights tomorrow from Stockholm to Los Angeles. And then you might also say like, by the way, this travel example, I think is really underserved. If you kind of look around and see what's offered. So a lot of times the question might be something like, you want to go to some travel site and you want to ask like natural language questions like, okay, what are the direct flights from Lixela? Where do the direct flights? Where do the direct flights flying out of Umeå? Where do they go to? And it's pretty much Stockholm, I guess. But then there's some other ones that come up. What are the charters that leave from an airport within 200 kilometers of Arlanda? What destinations do charters fly to in the month of November? Right. So these are like natural language questions that you can imagine. Like, I think that ultimately AI will serve those kind of questions because those are the kind of questions we want to know about, right? A lot of times you go to SAS's website and it's just like, you can't pull those out. You just have to go through their forms. So the idea of more of a customer facing example is like travel databases, right? Where you can use natural language to ask just kind of, questions like, instead of like putting in the date, say tomorrow, like tomorrow is always like a known date based on when you ask the question. So it would be kind of nice to be able to have natural language there. So this is kind of motivating the need for some type of text to SQL capability. So the problem has been around for a long time, a very, very long time. So there's kind of like you can basically divide it into 3 periods. There's like before what's called WIMP, and I'm not sure if you guys have heard this term WIMP before, but WIMP stands for Windows Icons, Menus, and Pointers. So that came about like with the Apple Macintosh. Well, I mean, you guys know the whole story, right? I mean, it came out of Xerox PARC. Xerox PARC innovated the idea of using these kind of direct manipulation interfaces with Windows icons, menus, and pointers. Steve Jobs took a tour of Xerox PARC. Xerox PARC was a big, Xerox was a big kind of like dinosaur company that it didn't want to like innovate. They had some kind of monopolistic position so they could fund research. And they did that at Xerox PARC. Steve Jobs came along, he saw it, and he said, "Oh, I'm going to build this." He built the Macintosh. That was like in the 85, 86, something like that. 1985, I believe. 84 maybe. And then slowly but surely, then Windows 95 came along, 1995, etc. So basically, this whole kind of thing, let's just call this as like post, when it really got started, post 1990. This is rather pre-1990. Pre-1990. So there was a lot of work before that, where they thought, we'll use natural language to access information systems and to do commands, etc. So we basically say there's like a lot of research happened in this era here. It was like a big area in research of doing natural language interfaces to SQL. So text to SQL or text to some database access was very popular as a research problem. And also some commercial products too, pre-1990. Then, of course, Windows, the WIMP stuff was so successful that it kind of clobbered the text to SQL work. And now we're seeing a bit of a revival with the chat interface kind of making a comeback. So that in the large language model here, which I would basically say starts in let's say 2017. So that's when this starts. Okay, so we got from 1990, we've got pre-1990, before 1990 is this period. Then we have 1990 to 2017 is the middle period. And then the LLM is 2017 plus. Okay, so now the approaches that we're going to look at, we're mostly going to be looking at LLM-based approaches, although I do want to bring up this alternative 3, which is kind of a little bit orthogonal or opposite or dual to the LLM approach. Is basically a combinatorial match. And my system is C-phrase is based on this, but it's also hybrid, so it takes in some of the LLM stuff. Anyway, the core approaches are basically to text to SQL is just doing it as a 0 to a few shot prompt. So basically what you do is you say, here's the schema, and here's the question the user has, and then please LLM. And maybe Claude is maybe the best at doing this. I'm not sure. I haven't tested Claude recently. But yeah, give me the SQL that this represents. Okay, so that's a few shot prompt approach. So this is really the kind of the game in town when it comes to LLM. So you have to, now you might have a more and more sophisticated prompt here, but you put this into an LLM or an LRM, right? So in our terminology, an LLM is a large language model or a large reasoning model. Okay, so you put that in, and then it pops out the SQL, which then you presumably evaluate over the database to get the answers. Another approach is a very is a much simpler approach, which is basically based on semantic search. So you have a whole bunch of natural language SQL pairs, and then you feed that into a vector database, and then you basically when the user's question comes in, and then you find the SQL that is the closest to the user's question, and that's what you execute over the database. So those are the two, and then we'll talk a little bit about common term match based on how much time we have. But what I want to do is I want to talk a little bit about the history here because I think there's a lot going on. And then, of course, when this thing was, we'll conclude. Okay, so the history of this, like I said, it's a very long history. And if you guys are aware, like Ted Codd was pretty much the innovator of relational databases, but the ideas behind relational databases are coming from kind of the developments in first order logic that would kind of happen throughout the early and mid 20th century. Anyways, so Ted Codd also conceptualizes. It's hard to say how far they got with implementation since it was in the late 1970s. It was very kind of rudimentary. But there's a system called rendezvous, which was, I think, really is unfortunately it doesn't get much attention, but I think it really kind of talks about a lot of the requirements that we really need for these kind of systems. So the idea behind it was that the user asks their question, right? And then the system always has to paraphrase or describe back to the user. So I'm the user, right? And I have my question. And this goes into a system which then produces SQL, and what I'll say is a query. Okay. So when I say question, I'm usually talking about the text. So something like, give me the flights from Arlanda to somewhere sunny tomorrow. Okay. The query is the actual formal like SQL that's going to get evaluated over the database. But the paraphrase, this is the paraphrase. Oops, sorry. The paraphrase is you want flights from ARN to, and then I might say Spain, Portugal, okay, etc. So the paraphrase is the system interpreting the user question. So the question being, give me the flights tomorrow to somewhere sunny from Stockholm. And the paraphrase is what the system, this black box system, right? This is a kind of a black box, what that system mapped it into. So this is a natural language generation that describes the SQL that's going to be evaluated over the database. And so the argument here, and it's an argument that really needs to be made, is that if you don't have this step right here, if you don't have that, and all you do is take the user's question, you take the SQL, you evaluate the results, and report back the results, then the user lacks confidence in the quality of the result that's coming back because they don't really know how they were interpreted. If you accurately paraphrase back in natural language what the question was, then and how it got interpreted, then you're going to have a better user experience, the user is going to have more confidence in the results that come back, or they're going to have some confidence. And of course, this gets particularly vivid if you talk about like some kind of like somebody working in an ambulance or something and like trying to get kind of information. So you need this. So I hope that makes sense that this facility is really critical to any kind of real system that's going to be going to be deployed in the real world. You need to have some notion of kind of giving a reassurance to the user about how they were understood. Surprisingly, a lot of subsequent work just skips this, which is really bad. But of course, they're just kind of focusing on the pure problem. But this is really kind of a critical thing. So even some systems were deployed where they would just flash the SQL that was getting evaluated. But that's a cheap way of doing it. But that's going to not work for a lot of cases where people don't understand or know SQL. So anyways, another advantage to this kind of ability to generate paraphrases, which Todd talked about, is the ability to resolve ambiguity. So a lot of times if you say something like, give me a good flight, or give me something, that I mean, I think that's a good example of saying, give me something good, give me something that is popular, something, you would say something like that. There can be lots of notions of different what it means for something to be popular, what it means for something to be good. And so that kind of actually is ambiguous when you ask about that. It's like saying something like, give me a big city. Okay, or give me a big country. I say, give me a big country. Wow. Do you mean big by population, big by area? What do you mean exactly? So this ability, this fact, the fact is that natural language is inherently ambiguous. And a lot of times what you need to do is you need to have dialogue that's going to resolve the ambiguity. So a lot of times when you ask for something, then again, using the paraphrase mechanism, the system might say, oh, do you want like the big countries population-wise? Do you want the big countries area-wise? Okay. So again, that's again showing that the paraphrase ability. And so these kind of capabilities, these are something that haven't gone away. I mean, just because you have LLMs doesn't mean that these things are still not true. These are true. Okay. Another thing also that you need to do, and I think LLMs are pretty good about this, is that when you look at what users actually type into systems, anybody who's deployed any of these systems, and I have, and I've seen kind of what users type in or what they click build or whatever. You have to be able to handle the non-grammatical slop that humans actually type in. So a lot of people will put in kind of like very short little phrases that are not like grammatical and that are just kind of trying to hit. Like for instance, I might say like cheap flight, Spain. Okay. Well, do you mean cheap flights from Spain? You mean cheap flights to Spain? Okay, that's ambiguity again. But cheap flight Spain is not English. It's not like a nice kind of like clean kind of grammatical sentence or grammatical question. Okay. And the reason why this has to be kind of dealt with and countenanced is the fact that, as we'll see when a lot of the work that goes on, the work that went on in it, is that people were trying to kind of like make things grammatical, and they ran into a lot of problems because their system had some expectation that things were going to respect the line, the rules of syntax. So there has to be some kind of relaxation in terms of accepting non-grammatical inputs. Okay, I think LLMs will be pretty good at that. Right. Okay. So there was a lot of effort on these kind of problems in the up to like the let's say 1990. It's the 80s and the 90s were really the kind of heyday of this. So it's before WIMP. Well, in 1978 we had this Waltz system, which is like one of the first semantic grammar systems. And then what happened actually is we got to this issue with these transportable approaches. So these were really the transportable approach was really kind of like the state of the art for these kind of systems. So basically what transportable approach would do is they had these general grammars. So here's the user's question. And they would put it through a general grammar because a lot of work was going on in linguistics at that time trying to develop grammars in computational linguistics. And that would then give you a syntax tree of the actual sentence in terms of like things like noun phrases, okay, verb phrases, noun phrase, adjective, noun, prepositional phrase, this kind of thing. Okay. That would, of course, be bounded here, preposition and a noun phrase. Correct. Okay, so if anybody's familiar with kind of like linguistics or computational linguistics or syntax, so this is a syntax parse. And the idea is that they were developing general syntaxes that covered the full human language. Like they generated like linguistic theory was telling us at that time like how we can generate kind of fully capture the syntax of like English or Swedish or something like that. So a lot of work was going on that. And the idea is that from that, then you would have a specialized system that would then map this to SQL. Okay, so this was kind of nice. It was dovetailing different areas of research into one another, and it kind of culminated in this team, the team system. Now, the problem with this, of course, is that how does it deal with a non-grammatical slop? All right, so that's kind of a side question. How does it deal with non-grammatical slop? And then also like, well, what's this transportable knowledge? What is the form of this knowledge here that maps from these syntax trees to SQL? The whole thing. Well, and anyways, it was very advanced, but the question is, did it really, it looked nice in theory, but then in terms of building the systems, it was very difficult. And so these were very, very brittle and kind of, again, this is what happens, unfortunately, in the research world is a lot of times people will kind of go in the kind of like push these kind of things through, but there's like, from the software engineering point of view, it's kind of not very feasible. Another topic that was really interesting in that time was this issue of cooperative information systems. And in fact, I did some work in that period in that. So I was just a little guppy during that period. But I worked in Wesley's group at UCLA in cooperative information systems. So cooperative information systems is very interesting. So when you look at this right here, this is kind of like, if you go back to okay, so there's like two main people in like linguistics or computational linguistics that need to be kind of talked about, is Chomsky, who deals with syntax, and then we have Montague. And Montague was doing this business of like Montague was doing this business of basic computational linguistics, where you have what's called logical form that kind of plops out of these systems. Now, another important figure was Grice, who talked about something called conversational implicature. So the idea behind this is, and this is what cooperative information system was really taking the work of Grice and then dealing with kind of what some of the issues were. Okay, so for instance, let's make a concrete example here. Let's say that I asked you the following question. I say, give me the males that are under 18 that have a staph infection. Okay, that's a particular type of infection in Ward Z. Okay, I want the males that are under 18 with a staph infection that are in Ward Z. Okay. Now, let's assume now, just as an aside, that there are no patients whatsoever in Ward Z. Ward Z is vacant. Okay? Ward Z is vacant. What should be the answer to the question? Give me the males under the age 18 that have a staph infection in Ward Z. What should be the answer? The answer should be, okay, the answer in a literal sense, if you just take kind of a direct, natural language SQL kind of mapper, it'll be none. There are none. But that's a misleading answer. The correct answer is there are no patients at all in Ward Z. Okay, so that right there identifies a cooperative technique where you basically report the minimal failing subquery. So in this case, if you just pull off all the conditions of the query except Ward Z, and you're still getting no answer, you should report that. You should report that there are no then when you put the condition Ward Z, there are no patients. So I hope that people see that as kind of that's a more cooperative response. And there are theoretical reasons why to talk about that. There's this whole notion of what are presuppositions that are in question. So when I ask a question, there's a presupposition of existence in that there should be an answer to that. Because I'm asking about the men under 18 or males under 18 that have a staph infection in Ward Z. When I ask that, there's an expectation or a presumption that there should be some answers to that question, but there aren't. And in fact, what we do is there's also a presupposition that there are patients in Ward Z when I ask that question. So all of the subqueries of that, all the generalizations of the query, I'm presupposing that there's existence for those. And so what this minimal failing subquery strategy does is it will report the minimal failing subquery. So so basically this whole topic of cooperative information systems is part of what's called pragmatics in linguistics. Pragmatics. So a lot of times in linguistics, there's syntax, there's semantics, and there's pragmatics. Okay, those are and then there's also morphology. There's if you look at modern linguistics, there's this kind of talking about this pragmatics. But pragmatics is definitely part of real systems. Minimal failing subqueries is one example. There's other examples also, and that is like, for instance, a very, very there's query relaxation. So which that we did some stuff on query relaxation. So I'm looking for a particular machine part that's under a certain weight that satisfies this power requirement, that does this function, that is this color, that is made of this material, that costs under a certain price, whatever. I lay in all these conditions, and the answer is None. Because I overly specified the set of conditions on the question, and there are no matching results. So what relaxation does, which is again a cooperative behavior, is it will systematically loosen the conditions and search in the neighborhood of the query, looking for something that might match, and then it will present those alternatives to you as part of a cooperative response. Okay, another example of a cooperative. So there's a whole bunch of different cooperative techniques. So that was relaxation. Another one's association. So like for instance, if I'm asking for hotels, maybe I want to also ask questions about rental cars. That's an association. And then there's also topics of kind of just like especially when you think about like speech interfaces. If I say something like, "Okay, give me the shirts," like I go to a men's somewhere I can buy shirts online. I say, "Okay, give me the shirts," right? Okay, there might be like 1,000 shirts in there. So what it really should do is it should summarize and break it down as a kind of break it down as a series of the response should actually be, okay, there are do you want a collared shirt, collared formal shirt, do you want a polo shirt, or do you want a t-shirt? Okay. And I say, oh, I want a t-shirt. Okay, now we're talking. And then we can kind of we can do a dialogue until we get to a reasonable number of options that then can be presented to me, rather than just give me a giant list. Now, in terms of giving a giant list, that might actually make sense if it's just kind of like a standard kind of web interface or something. But if it's a speech interface, you definitely can't do that. So I can't start reading off all the options, right? If there's like 50 shirts, I mean, and I'm going through like a speech interface to kind of get to the right shirt to order, that would not make any sense. I would want to only be presented a list when the list size is small enough so that I could actually deal with listening to it. Okay. So those are all kind of cooperative behaviors. And so cooperative behaviors, again, those kind of behaviors are going to be, just because we're talking about LLMs doesn't mean those things are going away. So this kind of work in this kind of pragmatics, this kind of work is still very, very relevant. Okay, so we get to the point though at the end of the 90s or whatever, or I'm sorry, in the beginning of the 90s, where we have really this is in the 90s, two really important papers that talk about the evaluation. So they talk about, okay, well, all this work has been done, all this money has been invested in these things. We have a couple of commercial systems that have been deployed. They're doing natural language over databases, et cetera. How well did they do? And the answer was it was very disappointing. So the adoption was very disappointing. So you can read about this. So these are some links out here. So this, so all of these are links here that go. Copestake is a particularly good one. Ogden is very good in terms of evaluation techniques. It talks about how do you actually evaluate these kind of systems. And evaluation is, again, something that's not going away. It's still very important. But basically what happened was that one of the main problems with this natural language to database to SQL problem interfaces was that it wasn't really clear what the linguistic coverage was. So what could you, like, you're given a system that, let's say, for instance, has travel data. I'm not really sure, can I actually ask about, I could say flights, can I talk about, like, what words can I use? Okay. And then there's also so there's two different types of failures, essentially. There's a linguistic failure. So there's a failure in parsing and taking the way I put the question and putting that in SQL, but the concepts are supported inside the interface. It's in the database to get to it, as opposed to questions where I'm actually asking for things that are outside of the scope of what's being covered in the database. So that's basically this difference between linguistic and conceptual failure. And the problem with these systems is it was very, very difficult for them to kind of let the user know in a graceful way if it was a linguistic failure or if it was conceptual failure. Should you put the question in a different way, but the information is in there, or are you asking for information that's not available in the database? So that having it so that people can distinguish between those two, or have it so the user can kind of understand what is available, what's not available, is really critical. And when it fails, it really results in lots of frustration out of the user. The user gets very frustrated when they can't tease out what the problem was. All they're getting is that it's failing. Okay. And notice one thing also that, okay, you might say, oh, that's not true anymore with LLMs, but it is when we start talking about agents later. So what are the actions that actually you can ask for? the system is going to have to be able to kind of describe that back to you as you kind of like work and negotiate and kind of adjust to kind of to put an order in or something. So this stuff is not going away. These topics are still very much alive. Another thing also, and this I think is again something that we're going to face in the LLM world, is that actually typing is not, it's kind of a chore, it's a pain. Sometimes you'd rather just kind of click on something, right? Click a link rather than type what your request is. So a lot of people just say this sucks having to type everything out, especially when when it's like the thing is so brittle. And then finally, of course, is that when you build these systems, it's very like there's a lot of tedious configuration. So you have to actually kind of build up like and configure the system to do what you want it to do. And an analog to that in our more modern time will be like getting data, getting good training data. Okay. So like the big boys, like the big foundational models and all that. I mean, how much of their time is spent okay, they're not configuring stuff in a tedious way, but then it winds up being that they have to kind of massage the right data, and collect the right data and put it into the right form. And the problem with all this like tedious configuration and getting good training data, this is a cost. And then there's a benefit. The system is supposed to give you a benefit, but this is a cost. And as we all know, you've got to get to a point where the benefits are more than the cost. That's the only way toward viability is that the benefits exceed the cost, right? So the cost is being hidden right now, as we all know, because there's a bunch of sucker investors who are dumping all their money into it. But what happens when those suckers are no longer willing to dump money in? So then it's really the technology has to be to a point where that it's a good, the benefits are being cost. It has to be accrued for, right? Benefits then have to be greater than cost, and then because of that, then you get profit. So. Okay, so there's another so again, concurrent with all this, so one of the reasons why things were so disappointing for the natural language over database stuff during this period here was because of WIMP coming along. So these direct manipulation interfaces. So I'm not sure how many people have like come across Ben Schneiderman's 8 golden rules, but these are kind of like really kind of succinct rules that systems should respect. So user interfaces should respect. I think it's really kind of a nice kind of crystallization of these. And these, of course, tend to kind of work well with WIMP type interfaces. But just to kind of what Schneiderman would say, and this has to do with back in the day, there was an argument about software agents, right? So this stuff is, again, reoccurring. So Schneiderman was on the side of direct manipulation interfaces, whereas Patty May was on the side of software agents. And there's an interesting link here to an older paper on that. But basically what Schneiderman says is that people are unwilling to trade reliable and predictable user interfaces, like direct manipulation interfaces, which are reliable and predictable, for intelligent but unreliable ones. So it's just like that feeling of like, well, I'm going to ask this system's going to learn about me and all that, and then it's going to go out and it's going to be booking my travel. It's intelligent. It's very intelligent. But do I really trust that thing to book my travel? Or would I rather go in and actually just kind of be able to do it myself? Or is there some kind of mix of these that might be the way through? So this is very much, this is very much kind of a shot across the bow for the agent type stuff, which we're going to cover next lecture, by the way. So, so what Schneiderman's rules are basically are there should be consistency across the entire interface. So you don't want to like get the feeling that when you go to a user interface that it's just kind of bolted on pieces of different kind of interfaces with different styles and different kind of models of how to get things done. So that's usually kind of the sign of like a really kind of a sloppy job when it just feels like a bolt-on. When you click on something, then you take it to something completely different, interface design. You're supposed to get your work done there and then return back to the original tool, and then it just seems like everything's really kind of not very well melted together. So it's an integration issue. So, but that's something that people want, is they want consistency across the entire interface. And then there should be universal usability. So basically, the system should be able to accommodate novices. So that is, in other words, they should have like little kind of help menus that pop up, or little kind of, some elements here that kind of that pop up and then kind of guide you through, give you maybe a tutorial or something. And then they should also cover all the way to the expert. So there should be like shortcuts so the expert doesn't have to do a lot of tedious work to get things done. So you want to really cater to have universal kind of applicability across the full interface. You want that. Natural language is pretty good for that in a way, because yeah, it's. I mean, this is not really saying that it has to be WIMP. This is just kind of saying that this is kind of these again are the golden rules. Okay, informative feedback. So as you're doing operations, as you're doing things, you're getting feedback on the operations. You can kind of see that they're that it's confirming. So you're it's kind of building confidence as you go along. And then you also have dialogue yields closure. So I find that a lot of actually web systems on the net don't do this, which is really irritating. But a lot of times you'll get to the point where you finally click purchase the items in the in the basket. Then you put in your bank ID, and then the bank ID comes back with something, but then you don't get anything directly in the interface that confirms that you did the order. Okay, so this is just kind of bad design if you're not showing like closing off the operations with just kind of a final thing that kind of lets the user know that their operation has been completed, and that presumably that it's a durable. So it's a durable, kind of like an acid, right? Acid type thing. So it's durable, right? So they get the feeling that when it says it's in there, then it's in the database. So if systems fail on durability, so they tell you that something closed, but it actually didn't close, that's terrible. But that also happens. You should like have it so that users can't try your best to prevent errors, but in the case of errors, have it report them and handle them kind of in a graceful way, obviously. To the extent you can, allow for reversibility of actions. Go back and put things in reverse. And this right here is maybe the controversial one, at least with respect to agents and all that. And that is that, according to Schneiderman, keep users in control. So the locus of control always needs to be with the user. I personally prefer it this way. I really do not like. I've turned off all the notifications on everything. I don't want the thing. I want to be in control of my devices. I don't want them to disturb me. Of course, if the phone rings, the phone rings. Keeping having it so the user's in control. A lot of people are just like that. I'm one of them. I do not want to cede control over to some agent, especially some agent that wants to and let's be honest here. It wants the cheddar in my bank account. It wants to kind of get in there and pull out that cheddar. So I don't trust them. I want to be in control. And sorry. Okay, and then finally, there's this issue of just in terms of using the interface, we need to have it so that we don't overload the user's memory. So we need to keep kind of short-term memory load. So a lot of times you'll hear about 7 plus or minus 2. This is kind of a famous result, I think, from Gibson, that talks about how many different kind of concepts can a human being hold in their mind at once. And they said 7 plus or minus 2, but then actually work by Kaplan said, no, it's actually, that was a threshold report. It's 5 plus or minus 2. So it's basically, and keep the load and keep it simple, stupid. This is over complexity is the enemy. Okay, so these were things. So Schneiderman. So these are things that kind of successfully put the whole natural language over databases into kind of hibernation. So so what happened in the middle period? This is like post 1990. Okay, there was a continuation of the transportable approaches, and there was but the thing is, the transportable approaches, because of their reliance on grammar or syntax and the kind of its the fact that it was so brittle. A lot of people reverted back to hand-built semantic grammar. So Microsoft English Query was a tool that actually came and went fairly quickly. And there's a lot of work going on here, but I point out my own work here, which was in semantic grammars, but they were based on X-bar theory. So they were they were based on this is kind of like the yeah, I mean, I don't want to get into the history of linguistics here, but XBAR is kind of before the minimalist program. Um, this is I could talk if people want to offline, I could tell people what XBAR theory is. But it's kind of a nice linguistic theory, and I kind of incorporated parts of it into the semantic grammar uh, system. But then also, importantly, they started in with supervised machine learning. So there's a lot of work where it's like you'd have a natural language SQL pairs, and then you try to induce by machine learning a processor for that. So Mooney in Texas, University of Texas, Raymond Mooney was one of the initial. Yeah, his group was very active in that and kicked off a lot of work. But then there was another work, the semantic tractability work, which is kind of combinatorial match, which is what C-phrase or catchphrase is based on. And in fact, it's kind of related to the minimalist program in linguistics. Now, the original work in this was Anna Maria Popescu and then Orientazione and Henry Crooks. And what's interesting is they actually invited me. So they won the 20-year award from Intelligent User Interfaces. And they actually, it was very nice of them. They invited me along on their panel. So because I'm the one who kind of took up, I think, and probably developed their stuff. Well, they I was the one. I think I am the one because they had invited me to present that. And I have a video actually of the rehearsal for the UI, the Intelligent User Interface talk. So now this, of course, it's interesting because it's 2017, so this is right at the end of there's LLMs are coming along at that point exactly. But I still think there's a lot of interesting aspects of this. Now, time permitting today, I'll kind of cover this, but I don't know if we're going to have the time because there's, I'm looking at the clock here and seeing that we've, yeah. So let's see here. So, anyways, so now we're going to come into the LLM era. So I wanted to kind of talk about that, that kind of background. And in the LLM era, there's a really important data set that actually is guiding a lot of this stuff. So when we get back from break, so let's come back to break at 15 after, and we'll go over just quickly what the few-shot approach is, and then the semantic search approach, and then I'll also quickly maybe do the combinatorial match approach as well. And then, yeah, so so let's take a break now. I'll pause the recording, and let's be back at 15 after.
You're on mute.
Thank you very much. Sorry. Okay. Welcome back to the. Thank you for telling me I'm mute. Fortunately, there's a. Okay. Yeah. So now we're back on break. Okay. So there's now that we're in the LLM era, 2017 plus. One thing that came along, which is interesting, right about this time, was the spider data set. So actually, you're going to be using this in your recitation number 3. You're gonna see spider, and then really you're going to be looking at few-shot approaches. Maybe probably not on recitation 3, but this we'll describe these different approaches. Now, one thing to keep in mind though is that there was a supervised fine-tuning effort in some of this stuff, but we're going to largely bypass that. So the idea behind that would be that you have a pre-trained model, and then what you would do is you would then go and you would train it on examples coming in here, and you would kind of fine-tune it for those particular natural language to SQL pairs. And then it's kind of hard. I don't really think that people are going to be doing this, but I don't think so. But maybe, you never know. Maybe on some really small local models, this will be an approach. But we're largely going to bypass that. We're just going to be looking at the flat-out few-shot approach and the semantic search approach. So, okay, like I was saying, the spider data set is 2018. So it was developed by 11 Yale students, and basically it has over 10,000 questions. And it's over 200 different databases, and it's classified the different questions into four categories: easy, medium, hard, and extra hard. So basically, like, what are the number of cars with more than 4 cylinders? This is over a car database. That's kind of a fairly straightforward SQL. For each stadium, how many concerts are there? Okay, so this is kind of doing a group by, a little bit harder. Which countries in Europe have at least 3 car manufacturers? Okay, that becomes even a little more advanced SQL. And then this they say is extra hard because it has subqueries and probably yeah. So it's just kind of an and it's doing a aggregation. So it's just kind of like their own way of kind of rating the different classes of problems about the amount of difficulty. But we have this, so you guys are going to get like a full copy of Spider in Recitation 3. So you'll see it there. Okay, so let's just talk quickly about the few shot approach. So basically, the way the few shot approach works is it basically packs the database schema and the question into the prompt. Okay, and it might do some smarter stuff here where it'll try to make a more refined schema description. So if like the schema is the schema is like 1,000 tables, it might find like it might do like a pre-processing step to find the relevant tables to put into the prompt. And it also might put in some kind of data state just to kind of like help the system along. Because that's always like a tricky thing about data state, especially when you get to like really kind of cryptic schemas where, it's like, I mean, we'll see into this right here. Now the results are kind of mixed, but they're getting better. And we're going to notice in some code here that shows it, and this will kind of be a little bit of a warm up for recitation, because this is kind of, I'm going to fix this today, make it a little bit cleaner, and this will be part of your recitation, the code that you see in recitation, this SQL zero shot. Okay, the pros are that it's very low configuration costs. Okay, it's really low, but then the problems are that it does have reliability issues. And so the reliability issues is like kind of like, it's like with a lot of things. I mean, would if it could map to SQL 90% of the time, if it could map to the correct SQL 90% of the time, well, is that good enough? Is that good enough? Well, there's a whole bunch of design issues about how well it can be kind of put into like an application. Maybe some design issues can ameliorate this, but a lot of times you really need to have very, very high reliability in many application areas. It needs to be really high. And then a downside also is that it is slow relative to the other approaches. So let's just look at this some code here so that I can just give you a sense of kind of what this means exactly. It's really, it might be pretty obvious already, but let's just kind of go through the code here. Okay. So I'm going to share screen. Okay, so I assume opening it in the chat window. Okay, I assume you guys can see this. Put it in, okay, right, okay, I'm just going to assume that if you couldn't see it, you would say something. So first of all, this is Spider here. So if we look here, there's like, these are all the 200 databases. So there's like a database over Orchestra here. I've never looked at this, but if we look at the Orchestra database, we can see that it consists of the table of conductor, orchestra, performance, show.
I see the code, but I don't see where you're pointing right now. I just see the bottom of the code.
You just see the bottom of the code.
Yeah, like row 63 through 90.
Okay. Do you see like this? It says coffee shop.c phrase. You see that?
If not paraphrasing response is the first row I see.
Oh, sorry. Now I wonder how that happened. Yeah, so it says right here that my screen share has been paused. And then so this right here, This is an example, like I'm looking at this thing. This is an example okay, Zoom violates Schneiderman's 8 golden rules. I can tell you that right now. Because it's like it's got this weird thing. Okay, now I have to redo the share. Okay. The hell just happened? Man, this thing, it's just okay. I stopped the share. So you guys see my hand now, right? Is that true?
On your image that you share, yes, but not on the screen share. It still says you're viewing the
Okay,
screen.
so it still says that there's a screen share.
Yeah.
Okay, this is it's in real. Okay, so it maybe hid something underneath. Oh, one sec. Mute. Huh.
Now it's back to your hand. But now you're on mute. Maybe on purpose.
Nope, I was on mute because when you have to grab the stupid thing, it's very hard to kind of grab it without clicking on something. They don't give like a handle to actually grab the. I'm not sure if you guys know about this about like it's like when you have the little bar they don't have a handle on it, at least not in my version on Linux here. So you have to kind of be very careful to click on the boundary of it, which is very hard to kind of position the mouse for. So when I moved it, I actually clicked to mute myself by mistake. So this is again really like a crappy job, but I guess they're making them their money, so they're happy. But again, like I said before, there's a rumor that they have so much technical debt they don't dare touch the thing, and that's the reason why they haven't been able to fix it to make it better. So that's like must be wonderful to work for them as a programmer. Okay, so can you guys see it now? You can see the share now?
Yep.
Okay, and good. And you can see it says orchestra dot C phrase.
Yeah, and your mouse moving around, highlighting
Good.
table/table there.
Yeah, good. So for some reason, when I brought up, now the chat's not brought up, but here, let me just see this. Okay, I'm going to bring up the chat and then see if, and I'll be really pissed if it does this, but when I say, okay, now I'm nervous here. Okay, when I say chat, okay, it's still sharing, right? You can still see it?
Yes.
Okay,
Yeah.
good. I don't know how it got, I don't know how the screen share got paused, but probably because I was like moving, I don't know, and it's a terrible interface. Okay, anyways, enough of that, enough beating on Zoom. Um, although it does deserve it. Okay. Now, well, what we show here is that basically we show the whole spider. So this is what spider is. It's just a whole bunch of like schemas. And then if we look at orchestra, for instance, we see here that we have where are you? That's a bit strange. I go to I know that for airport at least. We have if I say aircraft rather. Yeah, we have aircraft corpus. I wonder why there wasn't. Okay, so these are like the kind of questions. So like this is actually an easy question here. How many aircrafts are there? Okay, what is the number of aircraft? So this is basically the question mapped to the proper SQL. So this is the SQL that it should. This right here, what is the average number of international passengers of all airports? That should map to this particular SQL. Okay. And then you might ask yourself, well, all right, what if my system mapped to instead of mapping to this, it mapped to the equivalent SQL x dot, and then this right here as x. Okay, well, if Claude or one of your particular systems is like actually using aliases when it does the mapping, well, when we do the evaluation, what we evaluate based on is what are the answers to the question. So pretty much any query that generates the same answers will be marked as correct. So we're not doing like a literal does the SQL exactly match? And we'll see that. Let me just back out of this right now.
So if my table airport is called TBL_airport, then what?
Well, this is this when it does the evaluation here, the airport is this right here. This is the schema.
Oh,
So
okay. Gotcha.
we'll see here. Let me just show you guys the actual like zero shot code. So SQL zero shot here. So how's it doing this? So the first thing you do here is you name which domain. So in this case, aircraft. Okay. So it'll go down into that particular directory and it'll pull in because each of those have a database in them. It'll pull that in. So now we have the actual connection to the database. This is SQLite we're using. The prompt then is given the relational database represented in the XML, and then it takes the schema of the database. Okay. Give the SQL in SQLite that answers the question, and then it takes in the question. And then answer, this is really cool, actually. I'm really impressed by this, that this actually works. Answer with only a JSON object with the key SQL that contains the exact SQL and the key paraphrase that contains the English description of the question. So that is really cool that it can actually do that. So it'll actually give you back a JSON object, and it does it quite reliably. So this is going into Llama. Here's your chain. This is kind of the same old thing. Then basically what it does is it'll read the schema here, and it'll print the schema. Then what we have here is it'll get the actual okay. This is an SQ. This is this corpus here, like this for instance, this aircraft corpus, or this is like a coffee shop corpus here. How many members of have black membership card? Well, I'll go to the aircraft corpus. So it actually will take this right here, and inside your zero shot stuff, it's actually doing a parse here, and that parse is an XML parse. Because this is if you look at this right here, this is XML, right? Okay. XML. And then so what it does is it basically takes this is from Minidom here. It'll give you the document object model of the actual questions. And now it's just going to basically count up the number correct, the total that number asked, and number failed. So all it will do, it'll just go through all those questions, and it'll grab out the question, the text for the question. It'll grab out the correct SQL right here. It'll grab out the correct SQL. And then what it will do is it will simply go through here, and it will, first it will actually give us the correct answer here. And then what it will do is it will set it up for the LLM. It'll put the question in as the question from the corpus, and then if there's no paraphrase or no SQL, it'll have some kind of errors that it can kind of report there. But otherwise, what it does is it'll actually execute the SQL over the database, and then it will generate a calculated answer. And if the correct answer, which was from the above, was from the original SQL, if that exactly matches the calculated answer, then it will print correct, and it'll add one more to the correct answers. And it'll just go through all the questions that way. So it's just basically doing a prompt, kind of a complicated prompt, and it's doing pretty much a zero shot when it comes to like just asking the question inside the prompt. Okay. But what's impressive is that actually this does okay. It does okay. So you guys will see when you evaluate this in the recitation that it's doing fairly okay with this. Okay. So I hope that makes it clear kind of what the simplicity, the ease at which this is achieved. This is very, very simple. Now, what you'll also do is you'll make this into a few shot to see if you can boost things that way. So a few shot will mean that you'll go to the corpus, and then you'll have like basically so the prompt that you'll develop here will be not only here's the schema and here's, given the SQL, give me the answer to the question, and here are some question SQL pairs that are correct. And you can go and you can grab all, as many that you can fit into the context window. You can grab other examples in the corpus, but of course, you don't want to grab the actual answer because then that will kind of violate the whole point of it. But you grab other questions around it to turn this into a few shot problem, and that should boost your performance marginally. Okay, and then another thing you can do is you can play around with like trying to shave down the schema representation so that it's only talking about the relevant parts of the schema to get a more focused kind of schema over which is constructing the SQL. Okay, so this will be pretty interesting to see kind of what results. And what I'm really interested in somebody doing, although I can't tell people to do this, I'll just mention it here, is that if somebody could, somebody who maybe has a subscription to Claude or one of the real professional, the real coding ones, if they could actually try to push theirs and see how Claude does, to see how the best LRM the best reasoning model is doing on these kind of problems. It'd be really interesting. And of course, if it winds up doing like perfect, then I'll be really upset because I'm hoping that it fails, to be honest. But you know, whether I hope it fails or I mean that's just well, we'll see, right? So okay, so but the thing is, I can't ask people to do that officially because that it costs money to run Claude, presumably. So, okay, right. So I'll stop sharing then. So hope that helped to kind of situate you guys for the upcoming recitation. Sure. Okay, and now we're back to this. Okay, so again, it's very, very low configuration. It's just like you just put in the schema, you put in the question, you say, give me the SQL. Okay. But reliability, yeah, and then it's not the fastest process. Approach number two. It's basically the input is a corpus of natural language SQL pairs, kind of just like Spider. And what you do is you take the questions the user puts in, and then you do, okay, so each of these, the corpus of natural language SQL pairs, you are going to take the natural language and you'll calculate a sentence embedding and put those into a vector database, just like we did with the RAG type stuff. Put those into the vector database, and then you pair that with the SQL it's associated. And then when the user asks a question, you simply find the nearest SQL, and then you use that. You just kind of put that in, right? So it's a little bit hard to evaluate because the thing is, okay, I mean, over Spider, because what you would do is we need things that are like questions that are close to the Spider questions that would map in. But it should kind of allow for you to kind of, if something is kind of a close kind of like linguistically close, like in one case I say, give me the total number of flights that have landed at a particular airport, LAX. And the other ones I say is how many airports have landed at LAX. That first query is indexed into the vector DB. Presumably, that should be the closest one, maybe. When I do the at real time, I take in the dynamic question of like, well, flights, number of flights arriving LAX. Okay, that hopefully that one will match the closest one. So I hope that the technique is really straightforward. It's just using a vector database in a very straightforward way. So it's a very easy implementation. It's very fast. And another advantage, and this is a big advantage actually, is it always gives answers. So it'll always find the nearest SQL and evaluate. The problem is it requires a corpus of natural language SQL pairs. And then, honestly, we need to deal with like this issue of named entity recognition or like dealing with templates. So if I say something like population of, and then I have country or city, right? So population, this is a templated query. So this is a pattern where I say the population of, and of course that maps to kind of a straightforward SQL, but the country is kind of like a named entity here. So it could be the population of Germany, population of France, population of Italy. So if you're going to take this kind of approach, you probably need to like do all the, it's difficult. I mean, you can conceive of ways to do this in a templated approach if you have multiple vector DBs. You could have one where you do well, I'm not going to get into that more advanced use case, but if you just kind of take a straightforward use case, you'll have to actually, if there's 230 countries or something, you're going to have to you have to unfold each of these, map them to exact SQL, or have them associated direct SQL, and put 230 queries into the vector database. And then if someone says how many people live in Germany, then well, it'll maybe give you the population of Germany, right? So how many people, population of, I don't know how close those are, but Germany is close to Germany. And then what happens if you put in Deutschland rather than Germany? Well, Deutschland should be close to Germany, so that should actually help as well. So, so you'll be able to kind of use like kind of all this latent kind of distance, semantic distance that's kind of coming from the web when it trained the actual sentence embedding. Okay, so that's kind of a straightforward approach. Okay, now the combinatorial approach, let's see, how much time do we have here? I feel a little bit kind of like, I don't want to go, I'll do it very quickly, but if people are interested, I'm interested because this is kind of the area I work in. Yeah, you can go and see the videos so that you can see kind of how it goes. So the claim is that it's kind of hallucination proof. potentially. It's very fast, so but it's a little bit brittle and it requires more configuration, but not a lot of configuration. It's kind of pretty good when it adopts the minimalist. The minimalist program helps with the configuration issue. And then it can be enhanced. So one of the things that I'm working on, actually I say we working on, my contractor and me, is to try to also have a semantic search kind of backfall in CPhrase. So that we've actually found that we had a customer that actually was doing some stuff with that because the problem was you don't want it to fail. You always if you backstop it with a template-based approach, kind of that approach number 2, then at least you're always going to get something. And in their particular case, they needed that. Okay, so I'll just do this very, very quickly. So in the combinatorial approach, what you basically do is you represent the database as a disjoint set. This is like a graph of relations, attributes, and values. Okay, so like all the values from the database. So this could be a fairly large graph because the values are coming in. So these are all elements, and then we also have the empty element. Then we have a set of words in natural language and phrases, which are all the finite non-empty word sequences. Okay, that's what a phrase is. We have a set of markers, which basically consist of focus markers: select, count, average, condition markers, rel, at, val, and marker stop. Oh, and actually, this thing I should mention. This is just kind of a little quick formalism that I did a long time ago, based on the 2017 paper. This has been extended to like update operations as well. So we have delete, update, and insert are also markers. Okay, and then we have a lexicon, which is basically just kind of these things pieced together. So here's an example schema where we have city, state, borders, flows through a river. So a river flows through a state borders another state, a city is in a state. Okay? And here's the lexicon. So what the lexicon does is it pairs phrases with basically markers. So this is basically markers with elements. So this is the lexicon. Lexicon is phrases paired with markers paired with elements. That's what it is. So in this case here, what is the marker select star and city? What is also paired with selecting star from state. And so this is overloaded, right? This is an overloaded kind of representation of all the ways that phrases can map into markers paired with database elements. So it's very, very simple in that sense. Okay, so why is it combinatorial? The reason why it's combinatorial is that a question is just a sequence of words, and then a mapping is basically maps to a set of, it's basically mapping from word positions to a set of marker elements. So these are in the lexicon. So basically, if I say, what are the cities in Ohio? What are all the possible mappings? Well, it's combinatorial. So the what could map with any of these whats. So if you go back to the what can map with that or that. Okay, there's two things it could possibly map to. What can R map with? R can map with, oh, here. R maps with basically the stop marker and empty, so it just kind of drops out. The also drops out. Cities then maps to just the relation, only can map to one thing. In maps to only one thing, potentially. Ohio then can map to a state name or a river name. Okay, so it just kind of combinatorially finds all the mappings. In practice, it's a little bit more efficient than that, but that's kind of what it's doing. Okay, so that's why it's called combinatorial. Now the thing is that there are a set of kind of axioms that mappings need to kind of satisfy. Basically, it's so things like, so we'll see in a second here what gets ruled out. So for instance, if I say, okay, select a state, okay, I want to list, so it means select star state, list what cities in Ohio. Okay, list what cities in, so these already don't match. So it's like are you asking for the state or the city? So this is already incoherent, and this gets kind of drops out of the selection. This violates the fifth axiom where it's saying, okay, I have a cities, that's good, a river, but then cities that should be in state here, where the state name equals Ohio. I have a river coming in here. So, but I'm asking for the cities, and there's no kind of linking here. So, because it has to go from city all the way to river, and there's no path, and it doesn't, you can't directly do that. So that also drops out. Okay, so there's these axioms that then will like basically remove certain combinations as just not being plausible. But there's a whole bunch that get generated. And this right here also showing how it's also relative to how many, so like bordering, it'll show that it can do joins. It can do kind of joins across bordering here. I'm not going to get into that. But basically, here's how it works. You have a lexicon, which is a very simple kind of object. It generates a set of mappings. These go through a set of axioms. And there's more axioms now, which gives us the set of valid mappings. And from that, we do the unfoldings to get the set of SQL expressions. So now, here's a conjecture, and that is if this is the true parsing function where we basically take the phrase and we map it to like a set of, a subset of the different possible questions, where Q is a set of SQL expressions over the database, the idea then is basically, it's a little bit complicated here, but the idea in words is basically if catchphrase or C phrase answers the question, so if it generates a set of possible SQL, then within that answer set, there is a correct answer. Okay, so it's under the suitable assumption. But basically, what this is saying is it's saying that it will always find a correct answer. Okay, but it might be highly ambiguous. So it might generate a whole ton of different possible mappings. And this one, we know that among those, if it does generate a set, then among those somewhere is the distinguished correct one under suitable assumptions. Okay, so that means that it always will find a correct answer. So it's not going to hallucinate. It's going to be in there, but the downside just might be that it's going to do it and generate lots to choose from. But in practice, though, it'll usually find it. Usually, you're not going to have that much ambiguity. Okay, so it's actually pretty effective. So that's a little bit of the theory that kind of supports the guide. So basically, the way you set this thing up is you basically you can bring in. You can calculate these attachments. You can bring in this kind of an off-the-shelf syntactic processor. And in this case, there might be a issue of bringing in something that's kind of an LLM. So an LLM can kind of like do some of the syntactic kind of constraint mapping. And then another thing also I brought in that I won't discuss right now is a theorem prover that just has to do with like whether or not the SQL that comes out is plausible. That's a whole other kind of story. So this is kind of a more a logic-based approach. But again, the thing to remember with this is that you can do all this and you can have a certain coverage, and then you can also augment this with a semantic search-based thing that's on top of it, so that if all this fails and it doesn't produce any set at all, because that's one of the things it can do, the answer that can come out can just be nothing. Okay, it can miss. In that case, you can then fall back to the templated semantic search approach. Okay, so that's kind of the hybrid, and then LLMs can kind of come in some other spots potentially. So the summary, the pros of this is it's hallucination proof. It's very fast. The cons are that it can be brittle and it requires some configuration. Okay, it requires a C-phrase configuration. But then we're working on this hybrid solution where we can enhance with semantic search and LLMs, and then also LLM-based wizards to speed up configuration. So it's kind of underway. Right. Okay, good. Well, that was pretty quick. Okay. So let's just conclude here. In this lecture, I think I've kind of covered in fairly broad terms, but I think fairly comprehensively the whole area of natural languages over database and its fuller history. And then, of course, I'll make the kind of Camilla statement here that a lot of fresh-faced LLMers are talking about text-to-SQL like they just fell out of a coconut tree. So I mean, sometimes I hear this, and I'm just like, I hear some people saying, I'm like, well, okay. I mean, you're a fresh-faced LLMer. Don't you know that you have to deal with like the whole issue of cooperative answers, and don't you have to? I mean, there's a whole bunch of things that just kind of come up, and you think, wow. And especially when it comes to some of the design stuff, and well, maybe it has more to do with agents, but it's just like, well, right, okay, Schneiderman. Another thing also to say about catchphrase or C phrase is that there's a lot, and if you go to the videos, you'll see it. There's a lot of design work that's gone in. Because again, my customers, I mean, like a lot of times what they really want is they want to develop these things maybe through C phrase and find some kind of templated questions. but they just really, all they want to do, what they want to do is they want to click on it, have it get evaluated, and then they might want to edit what's in the search field to kind of put it in a different constant to search for something else. So a lot of, I mean, in reality, people do not want to type so much, especially when you get into the kind of these kind of systems for back-end processes. People don't want it. They really don't want to be typing all the time. So I think that's one of the things that chat interfaces are going to really face, some of these design issues with this kind of stuff. But anyways, I mean, the LLM-based approaches are kind of in their infancy, so they hold great promise. Especially, I think what holds the most promise right now, and I'm going to try to get to the bottom of, are LRMs. And the reason why is because if you think about it, SQL results coming out of something is scoreable. It's scoreable. So LRMs should have an interesting impact. So we could conceivably see that, like, that because they can attach it to do a reinforcement learning kind of approach to the problem, maybe it'll get really good, but we'll see. We'll see. Semantic search is based on sentence embeddings, etc. There's a kind of an issue also of like, it's not really clear how this natural language to SQL subproblem, how that integrates in with the RAG pipelines. Okay, so there's a lot of kind of interesting work that needs to kind of be considered with that. But maybe we'll kind of like touch on that in the next two lectures. We'll try to kind of start looking at, I mean, in a way, we have to kind of look and see what's there, and then we have to start speculating about what could be to kind of handle these things. So anyways, that concludes text to SQL.